Okay, this is sort of a part notes, and we might do some problems at the end of this about partial pressure and vapor pressure. So all of this section of chemistry is about mixing gases, having more than one gas inside a container at the same time. So let's draw a container here. At this point, we're still talking about ideal gases. So we're going to assume that gas particles inside this container do not interact with each other, and they have no individual volume. Each particle has zero volume. And so if I draw some gas particles, okay, here's some gas particles bouncing around, and they all have some speed and direction. And then I have some different color gas particles to indicate they are not the same gas. And those guys are all moving as well inside the container. And according to the container, as long as these are all ideal gas particles, the container can't tell them apart. Okay? If one particle hits the wall of the container at a certain speed, the container doesn't know if it was a red particle or a blue particle, a red gas or a blue gas, because they're all ideal. They all behave more or less under the same set of conditions. Okay, that's the assumption we're making. Now, in the real world, that's not exactly true, but for now, we'll assume that that's the case. Okay, so in this sense, when we start talking about the pressure that the container feels, if you imagine that this container did not contain the blue gas and the red gas had a pressure equal to, let's say, 3.2 atmospheres, and then let's say that we didn't have the red gas, just had the blue gas in there by itself has a pressure equal to, 2.7 atmospheres. The container doesn't notice that. It feels 3.2 atmospheres of pressure from the blue gas, and it also feels 2.7 atmospheres of pressure from the red. Wait, did I do that backwards? 3.2 from the red gas, 2.7 from the blue gas. It feels them at the exact same time, and it feels them cumulatively. So, according to the container, the entire pressure inside there is, we'll see, P total would be equal to 5.9 atmospheres. That's what the container feels. That's the idea of partial pressures, that they all will add up to one total pressure. And I think you could do the equation like this, that the P total is going to be equal to the sum of P1 plus P2 dot 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 for as many gases, Pn for n number of gases, you could say, as there are inside that container. So you could put as many different gases as you like. If you add up all of their individual pressures, you will get the total pressure. And so in this case, what we will call P1 and P2 and all of those pressures from each individual gas, those will be called a partial pressure. It's a piece of the total pressure. So the partial pressure of the blue in this case was 2.7 atmospheres, and the partial pressure of the red was 3.2 atmospheres. All right? And they sum up. It's a very simple concept, really, compared to some of the other things we've learned in chemistry. Now, vapor pressure. Let's talk vapor pressure. This happens and is observed, and I'll make this actually, let's consider this an open container. So I have a glass, and I'm going to put some water in it. Okay, there's my glass. And then outside of the water are all these gas particles in the atmosphere that I'm drawing here in the air, bouncing around. Okay, there's the air. Now, water molecules have their own kinetic energy and move around. And if I were to draw them, I'm not drawing them to scale here, they would be much closer together than the gases in the atmosphere. But they're moving around. And occasionally one of those water molecules at the surface will have enough kinetic energy to leave the water mixture and become water vapor and turn into a gas, essentially. And now he will be floating around dissolved in the atmosphere along with the oxygen and nitrogen and everything else. This is very common, okay? That's called a vapor pressure. So that once that water molecule becomes a gas particle, it now is going to squeeze against everything else in the atmosphere just like all the other gases there. And so right at the surface of the water we have what's called a vapor pressure of water. We have some water molecules that have left the solution, or if it's not a solution, even just left the liquid, and are bouncing around above the surface there, along with the red atmosphere. That's just the general atmosphere anyway. Okay. Now there are factors that affect this. For instance, on a hot day, these water molecules are going to have much higher kinetic energies, and more of them will be able to escape from the surface. So this is a temperature-dependent phenomenon. The hotter it is, the higher the vapor pressure of water. And the lower it is, the lower the vapor pressure of water. So if you were to consider gases just above the surface of a liquid of water, and you were looking at their pressures, you would expect there to be a larger concentration, so to speak, of water in the atmosphere on the warm day than on the cold day. Okay, that may be intuitive. Now, when I want to know those pressures, you can look these up. So chemists have gone and taken samples of gases above liquid at all kinds of different temperatures that water can be at. Namely, water usually goes from 0 Celsius up to 100, because below 0 it's solid, and above 100 it's already boiled off. And so you can ask Siri. You can say, "Hey there, Siri, what is the vapor pressure of water at 10?" Whoops, I'll write this down, at 10 Celsius. And she will spit out an answer. I did this on my computer real quick. It said that at 10 Celsius, I would have 9.2 millimeters of mercury worth of water pressure. Or water vapor pressure. That's how many of these guys had escaped into the atmosphere and were pushing back. So if, for instance, the atmospheric pressure that day happened to be 750 millimeters of mercury, then we could say that on that day, and it was 10 Celsius outside, this would be a relatively cool day, depending on where you live. If the atmospheric pressure was 750 millimeters of mercury, and I went over to my favorite pond, I would expect the water vapor pressure to account for 9.2 millimeters of mercury of that 750. So, in this case, and we can make this into a little equation, the total pressure that day was 750, and the temperature being 10 Celsius meant that the partial pressure of H2O, the water vapor pressure, was 9.2. And remember, the total pressure is the sum of all the individual pressures of all the gases in that container, although in this case the container is just the air, right? I'm outside, I'm above the lake, that's it. So the total pressure would be equal to the water vapor pressure plus all the other gases in there. There would be some nitrogen and some, whoops, let me get rid of that there. Some nitrogen, some oxygen. Those are the two big contributors. There's also a little CO2 and a little argon and some trace elements, but those are the two big ones, nitrogen, oxygen. And so if I wanted to say, well, water accounts for 9.2 millimeters of mercury, what is the pressure of everything else? I could come down here and say, well, the total pressure was 750. That should be equal to 9.2 from the water plus everybody else. So this would be the pressure of the remaining gases. And if I subtract that out, I would get something like 700 and is that 40.8 8 would be the pressure, and this would be millimeters of mercury. That's the leftover pressure from the nitrogen, the oxygen, all the things that weren't water. Now, where we're going to use this, especially this week in our lab, is like so. We're going to take a reaction in a flask, okay, with some vinegar. Vinegar is acetic acid, about 5% acetic acid, and then about 95% water. So most of the vinegar is actually water, and only a little bit of it is the acetic acid. And into this acetic acid, we're going to add, so let's say this is the acetic acid molecules here. I'm going to add in some of this red stuff here. And I'm going to say, let me make a key here. The blue will be CH3COOH molecules, that's the acetic acid. And the red is going to be baking soda, NaHCO3, or sodium bicarbonate. And they're going to react. We've done this reaction before. They are going to produce a gas, however. Now, if I had sealed this flask, with a stopper or something, then when they react, the gas that they make is going to bubble up into here and fill this chamber. Now, what's also going to be in there, though, is some water. So inside this part of this chamber, we're going to have the gas that we're making, which happens to be CO2, but that's going to be mixed with some H2O as well as the atmosphere itself, assuming I didn't have a vacuumed out chamber. And we have to account for all those gases in our PT. It would be pressure total would be equal to the pressure of the CO2 plus the pressure of the water plus any other gases in there. Now, to avoid this problem, here's what we will do instead. We're going to take that flask, so here's our original flask, and we're going to stopper it off, but there's going to be a little connector here. Alright, we're going to bring that hose over like so, and we're going to submerge that hose in some water. And let me expand on that a little bit. Bring it all the way down in here. Pretend this is all one solid hose. And it's going to go up into a test tube. So you'll have a test tube like this that's under the water, with the hose going up into it. And so you can probably picture that now, right? Hopefully. So now, here's your two reactants, the red one and the blue one, and they're going to react and they're going to bubble off this CO2 gas. It's going to go up through this container all the way down, and it's going to bubble up into the top of this test tube. Now, as you do that, you will get a larger and larger space, right? That is completely not water anymore. It's just going to be bubbles of CO2. So the CO2 is going to start creating this space at the end of the test tube. And it will be the only gas there. Or will it? Because notice that you have this space with all those CO2 molecules, but it's above that layer of water. And since it's on top of water, again, water molecules being what they are, I'll draw on some blue water molecules here. They all have little kinetic energy. Some of those water molecules are going to escape from the surface and join those CO2 molecules. So what we will have at the end of this test tube is a little bit of CO2 and whatever water molecules can escape from the water, whatever water vapor pressure there will be. And this will depend on the temperature that we have. So our equation will look like this. The total pressure inside of that test tube will be equal to the pressure of the CO2, but it will also have to add in the water vapor pressure. which we will ask Siri for. We will just say, hey, it happens to be 25 Celsius today, or whatever it happens to be. What pressure of water can we expect? That's something we look up. We will also know the total pressure, because the total pressure is the same as all the atmospheric pressure that's pressing down out here. Okay? That's what's causing the total pressure. So we will have a total atmospheric pressure, and we will also have a water that we know, and we will also have a water vapor pressure that we know, and that will allow us to calculate how much CO2 we've collected. Now, the next step to go with there is if you knew, let me write this in, if you knew the pressure of the CO2 and you knew how much volume of CO2 you collected, which you could easily measure, right? If you went up here and you took and measured that distance, you could also be doing this in a graduated cylinder instead of a test tube. If you did this in a graduated cylinder, you could actually measure how many milliliters of bubble you had inside that graduated cylinder. Okay, you could get a volume. So you would have a pressure and a volume. If you also had a thermometer and knew the air temperature, or the room temperature at that time, you would have the temperature that the CO2 was collected at. And then if you knew the gas constant R, which we all know, you would have 4 variables by which you could then calculate the number of moles of CO2 that you had collected. That would be pretty powerful. And if you knew the number of moles of CO2 that you collected, you could do a stoichiometric calculation in order to determine how much actual vinegar you had in the first place, or how much baking soda, depending on if you knew one or the other. So this PV equal nRT equation, also involving the partial pressures and Dalton's law, is another way for us to get to moles. So if you remember last semester, we had a lot of different ways to convert to moles, from grams and from molarity, from atoms. We now have a PV nRT way to get an amount of moles that we can use for a stoichiometric calculation. And the practice problems you're going to be doing today are based on that concept. So keep in mind this equation, the law of partial pressures, and don't forget your PV equals nRT.